Hello dear students, let's start lecture number 6, that is electrolytic cell. So till now we have completed about electrochemical cell, Nast equation, thermodynamic related problems, PYQs, everything. If you not watched, you can watch those videos and can continue with this. I am pretty sure watch those all videos, surely it helps. So coming to electrolytic cell. Electrolytic cell is a device in which electrical energy is used to drive a non-spontaneous process, non-spontaneous chemical reaction. So here we are using electricity to make the chemical reaction. So this process happens with external force or external electricity, so that this is an example of non-spontaneous process. And we already discussed electrolytic cell delta G value is greater than 0 and E cell value will be less than 0, so that it is non-spontaneous process. Let's see example of electrolytic cell. So here electrolyte is present. Let us take molten NaCl. It's molten means pure NaCl in liquid form. So the electrode which is connecting to positive terminal of battery is called anode, which indicated with positive charge. The electrode which is connecting to negative terminal of battery is called cathode. And electrolytic solution have ions Na plus and Cl minus. And the electricity started passing through electrodes into the electrolytic solution. So the ions of electrolytic solution go to respective electrode and deposit or liberate over that. So here we are taking NaCl as an electrolytic solution. So Na plus and Cl minus ions are present in the electrolytic solution, and the electricity is passed into it. So here anodic reaction and cathodic reaction we can write. There will be no change in the anode or cathodic reactions. Anode means always oxidation takes place, cathode means reduction takes place. So here at anode, Cl minus lose electron and becomes half Cl2. This will be deposited over the anode. Because anode is positively charged, Cl are minus ion, so it will go and deposit over the anode. So coming to cathode, that is about Na plus accept that one electron and becomes sodium, means it deposit over the cathode as sodium. That's how this process is going to happen. So coming to key differences between galvanic cell and electrolytic cell. Galvanic and electrolytic cell. So if anybody not watched previous lectures, you can watch completely. I have explained including questions, everything. So galvanic cell is spontaneous process because we didn't use external energy over there. So spontaneous process, delta G value less than 0, E cell value greater than 0. So but in this case we have used external energy, so that it is non-spontaneous process and delta G is greater than 0, E cell is less than 0. And here anodic sign will be negative, cathode sign is positive. Why I have explained reasons also in that video, you can watch. It is very clear and good. So here anode will be positive, cathode will be negative. This is very normal thing. So in this case, chemical energy converted into electrical energy, chemical to electrical, but here electrical to chemical. So these are the differences between galvanic or electrochemical cell and electrolytic cell. So this is overall what is the mechanism, how it happens. Now under electrolytic cell, we supposed to discuss two concepts. The first one is quantitative analysis and the another one is qualitative analysis. So what is quantitative analysis first? Qualitative analysis in the sense, suppose if you take molten NaCl, it contain only Na plus and Cl minus ions. So Na will go to cathode and deposit over that, Cl minus will go to anode and liberate over that. That's very simple. Instead of that, if electrolyte contain more than one ion, more than one positive and more than one negative ion, suppose you take aqueous NaCl or brine solution where water with NaCl, there more positive and more negative ions are present, H plus, Na plus, Cl minus, OH minus. In that case, which positive ion deposit over the cathode and which negative ion deposit over the anode? How to decide? That itself called as qualitative analysis. We'll discuss that after quantitative analysis. Just simple way, how much metal or gas deposit or liberate over the electrodes with respect to the charge is called as quantitative. Quantity, how much quantity, and what are formed is qualitative. So this is just basic definitions. Under quantitative we discussed two laws. Those are Faraday first and second law. Faraday first law, what it tells we will discuss. This is most important in this whole concept. And qualitative means how much deposit or liberate over electrode is nothing but quantitative. First law, the mass of metal deposited or gas liberated over the electrode is directly proportional to the charge passed through electrolytic solution. Charge passed to the electrolytic solution is called as Faraday first law. Very important and very easy, very simple, right? We have discussed here is when the current is passed, the electrode ions go and deposit over the electrolytic ions deposit over the electrodes. How much deposition or how much liberation over electrode depends on the current which we are passing to the electrolytic solution. If you pass more current, more deposition occur. If you pass less current, less deposition occurs. That itself Faraday first law. So what can be written in simplest way? Mass deposition is proportional to charge passed through electrolytic solution. So what we can write simple way, M is directly proportional to Q. So M equals to ZQ. So here Z is called as electrochemical equivalent. How to define this? The mass of metal deposited when 1 coulomb charge is passed, and 1 coulomb charge is passed to the electrolytic solution. Is called as Z. So here Q is nothing but charge, which can be written as I into T, that is current in amperes. I is current in amperes and T is charge. T is time in seconds. So here T equals to time in seconds. This is how we can write it. First law of Faraday. So here there is one more term called as E. E is called as chemical equivalent. Chemical equivalent. Equivalent is nothing but the mass of metal deposited when 1 Faraday charge is passed. 1 Faraday charge is passed to the electrolytic solution. To the electrolytic solution is nothing but chemical equivalent. So what is 1 Faraday charge? Charge of 1 mole of electrons. Charge of 1 mole of electrons. So what is charge of 1 electron? 1.602 into 10 power minus 19 coulombs into charge of number of electrons in 1 mole is Avogadro number, 6.023 into 10 power 23 electrons. If you multiply this, you are going to get 96,485 coulombs, is approximately written as 96,500 coulombs. This is how we can get the 1 Faraday charge. Now when we pass 1 Faraday charge to the electrolytic solution, whatever the mass of metal deposited is nothing but chemical equivalent. Now what is the relation between E and Z? E and Z relation you can see. We know that Z is the mass of metal deposited when 1 coulomb is passed. When mass, what is E here? When mass of metal deposited when 1 Faraday charge or 96,500 coulomb is passed. So how can we make relation between them? E equals to E by Z equals to E by Faraday or 96,500 coulombs. Now accordingly you can substitute in this. So M or W you can take. W M equals to, just you can take here. So here what we can write it is M equals to ZIT. So M equals to E by F into IT. So this is the important formula. So in the place of F we can also take it as M by F means 96,500 into IT. But here the metal deposition is not depends on the moles of metal. It depends on the number of electrons passed to the solution, means charge passed. So that's the reason what we can write it is, so M equals to E by so what we can write it is E equals to molecular mass by N factor. So this can be substituted in the M equals to ZIT. So M equals to E by F into IT. So E equals to molecular mass by N factor or oxidation state or N factor or valency factor, like different way of representation. Valency factor, so what can be written in the place of E? So M equals to M by, that is mass of metal deposited by M by N factor into F into IT. So this is the formula for mass of metal deposited. So here capital M is atomic mass of metal, I is current in amperes, T is time in seconds, N factor is oxidation state of metal, means loss of electrons, how many in the particular metal ion, and F equals to 96,500 coulombs. And small m is nothing but mass of metal deposited. So here next one is current efficiency. Hope it is clear. Current efficiency. So current efficiency is nothing but how much of supplied current is actually used for the desired reaction. How much of the current of the supplied current is actually used for the desired product. See here, we generally think whatever current is passed, that whole thing utilized in the deposition or liberation of electrolytic ions, but reality case won't happen like that. Some current is wasted due to some side reactions or loss of heat, or some gases escape over the electrolysis process. So that's why, so current efficiency may not be 100% all the time. So current efficiency formula, current efficiency or current capacity, we can indicate eta symbol. Percentage of current efficiency equals to actual mass deposited, actual mass obtained to theoretical mass into 100. This is the formula for current efficiency. So what we can write mathematically, eta equals to M actual. So M theoretical means what we do through the formula. So what can be written here, MIT atomic mass into I into T by N factor, that is oxidation state of metal into F. So that's how we can get the theoretical mass of metal deposited. So this is the overall what is the concept behind Faraday laws, that too for first law of Faraday. So additional point is equivalent mass, equivalent volume of gas, how to calculate. So there will be some trick here. Just O2 gas means 1 mole of O2 occupies how much, 22.4 liters at STP conditions. But what is the equivalent volume of O2 gas? See, equivalent volume of O2 equals to the volume at STP conditions from 1 mole is 22.4 liters by, like you can write volume deposited at STP conditions by N factor or valency factor. So how to write valency factor for gases? It's very important. So O minus 2, O minus 2, just assume the charge of every oxide ion is minus 2 normally. Without charge you just add powers. So 4 is the valency factor for oxygen gas. So what you can write, 22.4 by 4, which is equals to 5.6 liters. This is the equivalent volume of oxygen gas. Suppose if you take N2 gas, what can be written? Charge of each non-metal ion is -3. So what you can write, 22.4 liters by 6. Just you have to add the powers without sign. This is the trick, there will be no correct logic, just to simplify this question. So H2 or Cl2 or F2, if you take 22.4 by 2, because H2 means H plus 1 and H plus 1, like that. That's how we can find the equivalent volume of gases. So this is overall what is the equivalent volume and what is the formula of Faraday first law and everything. There is one more application for this. So very important application. The deposition of metal doesn't depends on number of moles of metal. It depends on the charge passed through the electrolytic solution. So what is meaning of that? Same charge, let us take 1 Faraday charge is passed through Ag plus Mg2 plus and Cu plus 2, or simple way aluminium plus 3 you take, Al plus 3. Then to deposit 1 mole of Ag plus, what we can understand is very simple. Whatever the charge is mentioned here or oxidation state for metals, that is most important. To deposit 1 mole of Ag plus, 1 Faraday is required. That means when we pass 1 Faraday to Ag plus, 108 grams of Ag will be deposited. Same 1 Faraday if you pass it through Mg2 plus, according to logic, to deposit 1 mole of Mg2 plus, how many Faradays are required? Since charge is 2, so 2 Faradays are required. If I pass it 1 Faraday, 0.5 mole of Mg will be deposited, which means 0.5 mole means 0.5 into atomic mass of magnesium is 24, which is equals to 12 grams, which means 1 Faraday if I pass it to Ag plus, 108 grams means 1 mole of Ag plus. If you pass same 1 Faraday to Mg2 plus, it deposit just half mole of Mg, because charge of Mg is 2. So to deposit 1 mole of Mg, 2 Faradays required, but passed is 1 Faraday, so the value is 12 grams or half mole. Same way if you pass it same 1 Faraday to Al plus 3, how much is deposited? Just calculate, just 1 by 3 mole of Ag plus, because see 3 Faradays required to deposit 1 mole of Al, because charge is plus 3. If you pass it 1 Faraday, what will be the result? 1 by 3 Faraday is required, which is nothing but 1 by 3 mole of Al is deposited. 1 by 3 mole of Al means 27 by 3, which is equals to 9 grams. So when we pass it 1 Faraday charge to Ag plus 1 mole, which is 108 grams. Same 1 Faraday if you pass it to Mg2 plus, it deposited how many moles? Half mole of Mg2 plus. Same 1 Faraday if you pass it to Al plus 3, 1 by 3 mole of Al is deposited. So what we can understand from this? So equivalent, you can write, mass of metal deposited is directly proportional to equivalent metal of the ion in the electrolytic solution. So same point, M1 by M2 equals to E1 by E2. This is called as which law? Faraday second law. So we can make a statement also for this. Second law of Faraday is same current or same charge passed through the electrolytic solutions which are connected in a series is directly proportional to mass deposited, right? Mass deposited or mass of metal deposited is directly proportional to the equivalent mass of metal. That's nothing but m1 by m2 equals to e1 by e2. So this is called as Faraday's second law. That indirectly tells first law only. So this is what is electrolytic cell, what is quantitative analysis, and qualitative is going to discuss after some problems of Faraday first law. So that will continue in the next lecture. Thank you. Please like and subscribe. If you have any doubt, you can comment.